So hello everyone, my name is Nyquist PRM124B1F024. Today we are discussing the topic of channels and spectrum, which comes under the subject of the data communication and guided by the Professor Shweta Devdas ma'am. So let's discuss about the contents in this. First, channels and spectrum. The spectrum is the entire range of frequency available, while the channels are the specific frequency bands. In data communication, the spectrum contains the entire range of frequency, while the channels having the specific frequency band which are limited. So first topic is definition and its types. First and second one is Nyquist Bit Theorem and Shannon theorem. Nyquist Bit Theorem, here we discuss about the noiseless channel and noisy channel. And third one is the data fundamentals and fourth one is the types of analog digital. So move on the topic of definition and its types. Spectrum in data communication. The term spectrum refers in data communication is the electromagnetic frequency which is used to transmit the data in various communication channels such as wired, wireless and optical systems. This spectrum is a crucible which allows the communication from mobile phones and Wi-Fi to satellite and radio communications. Let's move on the types of the spectrum. First, radio frequency spectrum. It is from the range of the 3 Hz to 20 kilohertz. It which is used in radio, Wi-Fi and cellular networks. Second topic is microwave spectrum, which is in satellite communication or long distance wireless transmission. Infrared spectrum for use in short range communication like a remote controls and infrared ports. Fourth type is optical spectrum, using a fiber optic cable for high speed data transfer. Okay. Next move on the data rate limits. It's nothing but the bits per second over a channel, which contain the three factors. First case is bandwidth available, second one is the level of the signal we use, and third one is the quality of the channel. It is nothing but a level of noise. Here we see the diagram of the data rate limits. Topic discussed in this section is a Nyquist bit rate for noiseless channel and Shannon capacity for noisy channel. So move on the Nyquist bit rate for noiseless channel. So we have the formula of bit rate equals to twice into bandwidth into log of base to the L. Here bandwidth is the bandwidth of the channel. L is the number of the signal level used to represent data, and bitrate is the bitrate in bits per second. This is the paragraph in short, that is the increasing the level of the signal may reduce the reliability of the system. Here it is the whole conclusion of this paragraph. Let's discuss about the questions and answers. First question. Consider the noiseless signal with bandwidth of 3000 of hertz transmitting a signal with two signal level. The maximum bitrate can be calculated as. Let's see the given data. Bandwidth of 3000 of hertz, level of the signal is 2, and we have to find the bitrate. So bitrate equals to twice into bandwidth into log to the base 12. So put in the equation, we have the bitrate equals to 6000 of the bits per second. Next question, consider the same noiseless channel. That is, in previous question we have the bandwidth of 3000 of hertz transmitting the signal of 4 signal level. Here we have the signal of 4. So find out the maximum bitrate. Bandwidth equals to 3000 of hertz and level of signal is 4. Here we given that. So put in this formula, we found that 12,000 of the bits per second. So move on the next third question. We need to send up to 65 kilobits per second over an oscillator channel with the bandwidth of 20 kilohertz. How many signal inverse do we need? We have the given data of bandwidth of 220,000 of kilohertz to 65,000 of the bit rate level of the signal we have to find. So put in this equation, we found that level equals to 98.6, sorry 7. Result is not the power of 2. Read this form. Let's move on the noisy channel Shannon capacity. In reality, the noiseless channel is come from the cloud Shannon in 1944. In reality, we cannot have a noiseless channel. The channel is a noisy. So capacity equals to bandwidth into log to the base 2 of 1 plus SNR. Here bandwidth is the bandwidth of the channel. SNR is the signal to noise ratio. The capacity is capacity in bits per second. So move on the SNR, the signal to noise ratio. The signal to noise ratio is the average signal power to the average noise power. So there is the two cases of SNR, high SNR and low SNR. Here we see that the a high SNR in signal, here it can be shown that like that. For noise it can be shown this, and if both they combine then it can be shown in this form. For low SNR we show that there is a low frequency for similar in noise and signal plus noise. So signal to noise ratio, actually it is a ratio of the wanted signal to the what is not wanted noise. A high SNR means the signal is less corrupted by noise. A low SNR means the signal is more corrupted by noise. So SNR in decibel equals to 10 into log to the base of 10 of SNR. So let's move on the first example. Here we have power of signal of 10 milliwatt and power of noise of 1 microwatt. So SNR equals to 10,000 and SNR in decibel equals to 40. We have the here note the value of SNR and SNR in decibel for noise to signal are infinity. So first question, consider an extremely noise signal in which the value of the signal received is almost zero. Here with that SNR is zero, so the band capacity becomes zero. Let's move on the example of 2. Here we have given that a bandwidth of 3000 of hertz. So SNR is also given 3462. So put in this formula of SNR. Let's move on the example of third. The signal to noise ratio is we have to find SNR in decibel 36. The bandwidth is 2 megahertz. So put in this formula of SNR equals to 10 into log to the base 10 of SNR. SNR equals to 3981. So move on the data fundamentals. What is data? Data is a collection of the raw facts, figures, symbols, or values that represent the information in computing and communication. Data is the basic unit that is processed, transmitted, and stored by signals. Here we have the example. First, discuss the characteristic of data. Raw form, representable, storable, and transmittable is the characteristic of data. In raw form, data by itself may not be carry much meaning until proceed. Representable is in text numbers. Storable is a memory or external devices. Transmittable is a cables or fiber wireless. Important data communication. Data is encoded, transmitted or decoded or networking, telephone, internet or wireless system. Data processing cycle includes the input, processing, storage and output and feedback. Modern relevance of the data. Data is considered the new oil in today's digital economy, used for decision making, automation, AI, and machine learning is also used in data. Big data, cloud storage, and real-time analytics. Heavily on fundamentals. Types of data. Analog data. It is a nothing but the continuous and various physical quantities characteristic. Smoothly and continuously over time. Examples: human voice in air, analog log, or traditional radio and signals. We have the point of to and think about the analog data. We have the sine wave, smooth and flowing with no average jumps. So digital data, Digital data is discrete and represents information using the binary code of series of 0 and 1 seconds. Characteristic, it is usually of 0 1, store and secure. The text, it is in form of the document, digital images, JPG, PNG, MP3 music files, data sent via email or over network. Looks like a square wave with sharp transition wave of high and one low. So thank you.